So we'll continue with this. So to get away from coins for a little bit, just we'll start with a real data set. So this is the iris data set. I think we covered it a little bit in one of the earlier lectures, and it's basically the standard data set for showing your kind of visualization tool or machine learning approach works well because it's classifying different types of flowers based on sort of the width of their petals and the length of their sepals and other sort of metrics like this. So potentially this is useful for you because it's a bit more like the data you're actually measuring and less like coin flips. So that basically what the data looks like is you have sepal length, sepal width, petal width, and you have a number of different flowers. So this data set comes with almost every machine learning package you use. It's built into KNIME and Python and R. So it's an easy data set to play with quite easily. And it's, 4 different variables and 3 different classes of things you're trying to group together. And that for some of the variables, the things kind of overlap quite a bit. So this is called a pair plot. This is one of the more kind of useful visualizations. And what this shows is each one of the variables on the x-axis and then each one of the variables on the y-axis. And so what it tells us is these diagonal components are just sort of histograms. And all of these other ones are just sort of, this is the x plot is sepal length, or the y-axis is sepal length, and the x is sepal width. And so that we see the length and the width are kind of mixed together for these varicolour and virginica flowers, but the setosa is quite well separated. And then if we look at sepal length versus petal length, we see kind of a similar behavior, but it's a little better separated there. And with petal width, then it's even more separate. And so this kind of is a nice, quick way to see which variables are actually telling us new information and which ones aren't. So we can put our data in there and just use pair plot. It exists in R, MATLAB, and Python quite well. And this lets us just sort of see what's present. And so one of the things, again, that's kind of the core focus of this is this idea of reproducibility. So it's a very broad topic. There's lots of sub areas. There's lots of kind of deep analysis you can do, understanding your tools really well, understanding how your tools fail, how to make environments really reproducible. And we won't get into that as much, but what we want to focus on is really for our analysis and how are we going to get our analysis packaged up so that sort of anyone, anywhere could follow our instructions and get within some tolerance the exact same results from our samples. And so, we don't want to have to tell them you need to buy exactly the same laptop that I have with exactly the same amount of memory and processor. You don't want to say you can get the same answers, but if there's a bunch of code that I have and I'm not going to share it with you, so there's actually no way for you to check anything. And then there's kind of no manual clicking, tweaking, or copying. So if you have them run the analysis and then click the largest object and then save that and then run this part and then highlight the region that you're interested in and then run this, it's going to be impossible for someone to get exactly the same results that you got. It's going to make that very challenging. And so the idea is to have one script or one workflow go from the image to the result, or the data set to the result. The basic idea of this is that we have kind of a script set up. So this is what it looks like in sort of MATLAB. This is what it looks like in ImageJ, in R, in Python. They all look fairly similarly. And we'll have specific examples of that in the exercises that you can look at. But that basically you have an analysis where you give it your parameters, you give it the input, and someone can get exactly the same results, and there's no interaction that they need to have. And so one of the first kind of metrics we have for how reproducible our measurements are this idea of the sort of interclass correlation coefficient. And so what this is just a very simple metric for looking at how reliably we're able to make measurements. And so we can take this iris data set and sort of look at the kind of sepal width as sort of our first variable that we'll look at. So we have these three different groups, and we have this metric that we're measuring. And so what we want to do is have a way of assessing how similar these groups are. And so this is a fairly good example of groups that aren't very similar, so low group similarity. And so there's a lot of sort of overlap between these measurements. We see that the smallest setosa falls kind of below the average of both of these other two categories, even though the average setosa is above it. Which means, if you were to take this point, it'd be quite difficult to assign a group to it, because it would look like it belongs much better in this category, even though it is part of this setosa plant. Similarly, we have groups with high similarity, where you look at like petal length, and you see that there's some overlap here, but these two groups are quite distinct. And so what metric we have for doing this is called this interclass correlation coefficient. And basically it's the variance among the group or classes. And, this, estimate with the standard deviations of the mean values for each group. So you take the mean of each group, and then you take the standard deviation of those means. And then this is the variance within the groups of classes. And so this is where you then take the average of the standard deviations for each group. And so 1 means 100% of the variance that you see in your data is between classes, and 0 means all of the variance you see is within classes. And so that we can quite easily take that and apply that to our data set, where we see that this low group similarity is 46%, and this high group similarity is 95%. So that's sort of what we'd expect. That this is distinguished a little bit, but not very good. And this one is then quite strongly separated, so that we're able to look at that in much more detail. And so really where this is important is when you're doing these, you're doing a number of experiments and you want to focus on one of your variables, that the first thing you really want to do is make sure this interclass correlation coefficient is high before you do any other analyses. Because if this value is low, then you're not looking at a variable that's going to be able to distinguish what you're hoping for. Or if you're looking at something very low, you might need to combine it or improve your filtering or improve your post-processing to kind of increase that value somehow. And so now what this kind of all leads into is this idea of tests. So the interclass correlation coefficient isn't a test. It's a metric that you can calculate. It's a good indicator, but it's not actually a test or a statistical test in that sense. And so for comparing groups, what we really need are tests. And so once we have a sort of assumptions and a hypothesis, we can use the tools of statistics to actually start testing it. So the first step in doing this, if we start with a very sort of simple two-group experiment, is to kind of come up with what are all the assumptions that are going into our model. And this is always important to kind of be clear about. What things do you assume are the same? What things do you assume are different? If you make measurements, at the Swiss light source at PSI, over the course of 2 years, you'll probably have to assume that the operation of this instrument was the same over those 2 years. But the reality is there was probably new detectors, there was probably changes to how the beam position, to the beam intensity, to some of the cameras. And so actually, most of the time, your assumptions won't be completely correct, but it's important that you at least list them off so that you're aware of which ones might not be correct, or that someone else is able to do this. Because often when you do statistical analyses, you just sort of say, I applied this analysis and here's my result. And it's all sorts of assumptions that are hidden behind that are important for other people to be aware of in order to decide if your analysis makes sense or not. The next is sort of establishing the null hypothesis. So I guess anyone who's taken statistics before should be aware of the null hypothesis, and that this is usually that both of the groups are the same. And so that's saying that when you have, a group of sick patients and a group of healthy patients, and you measure their weight, the null hypothesis would be they have the same weight, that there's no difference between them. And then the last part is the sort of calculate the probability of the observations given the truth of the null hypothesis. And so this, requires knowledge about probability distributions of the data. Modeling can be quite exceptionally complicated, and this is where everything can become fairly difficult unless you use really simple tests. So has anyone heard of the t-test or the student's t-test before? Does anyone feel comfortable explaining it? Or what it means? No one. Or just a very simple explanation for what it does. Why might a t-test be useful? Yeah?
I'm not sure if this is the one that we normalize to the zero value, or is it the z?
That's the z-score. Yeah.
Yeah, but
Okay. Well, so probably most, so the t-test is a wildly overused test that probably shouldn't be as used as much as it is. It's applied a lot in inappropriate situations. And I think the general agreement of the statistics community is that there are much better tests for most situations. But the reality is, you'll probably do the statistical analysis you're aware of, and it's better to be aware of and have some understanding of the t-test than be aware of nothing. So I think it's quite an important starting point, and I think it's a realistic test to actually be fairly comfortable with. And it's a nice test because it's built into Excel, it's built into kind of every tool that you might use. Google Sheets has it as well, and it kind of gives you a quick number to work with. It's certainly not the latest and greatest, and there should, if you have time and energy, you should definitely spend it to try to understand which tests might be more appropriate, but it's better than doing no statistical tests, and it's fairly easy to apply to a lot of different problems. And so that basically this student's t-distribution is kind of a trick, and what it allows us to do is we assume sort of stochastic variables. All the stochastic variables in our system are Gaussian, and that the t-distribution provides an estimate for the mean of the underlying distribution based on a few observations. And so what this kind of tells us is if we take, 10 measurements, and, or 5 measurements, and one of them is 5, and one of them is 7, and one of them is 2, and one of them is 3. How do we decide what we were actually measuring? So the mean of that, the process that produced that could be 100. Just like with the coin example, you could have a fair coin and still flip 5 heads in a row. That doesn't mean your coin is unfair. It's just an unlikely observation to have. And sort of what this t-distribution gives you is an idea of, based on the data that you've measured, what are the kind of likely systems that produced it, if you assume the producer of your data is sort of a normal stochastic variable. And so where this comes in is that when we look at this sort of calculate probability, calculate probability of the observations given the truth of the null hypothesis. What we have to know is we have to know what, given the observations that we have, what do we sort of assume about the system? And so, with the coin, if you're given 10 heads in a row, then your assumption is that it's not a perfectly fair coin, that, the average is, the mean is somewhere between 0.5 and 1, but it's probably not 0.5, which would be fair. And if you get 5 heads and 5 tails, then your assumption is the mean's probably somewhere, between 0.4 and 0.6, because you flipped it 10 times, and that's a fairly safe assumption to have. And so what the t-distribution gives us is the ability to kind of make some inferences about where the data came from based on what we actually measure. And so, we have this one coin in a coffee shop. We flip and observe independently. We assume they're all the same. Our null hypothesis, so that's the assumptions that we list off. Our null hypothesis is that the coin is unbiased. So our default assumption is that we get equal amounts of heads and tails, because that's kind of the information we go into it with. That's what you assume about a coin. And what you can do is calculate the likelihood of a given observation given the number of flips. And so that's what we ultimately call the p-value for the t-test. And so, if you get 10 heads, it becomes fairly unlikely that your coin is unbiased, but it's still possible. And so that's where we have, this very simple assessment that, if you flip a coin once, the probability of heads is 50%. If you flip a coin 5 times, the probability of all of them being heads is now down to 3%. And so this value sort of corresponds to what the p-value is for our null hypothesis. So if your cutoff is 5%, then at this point here, you're saying if you get 5 heads in a row, then I'm willing to say that this coin is probably not unbiased. You're now not saying what the bias is or how unfair the coin is. You're just saying that it seems very unlikely that this would come from an unbiased coin, or fairly unlikely, very unlikely, because 5% is 1 in 20. Now the problem, of course, with this is that if you have, by yourself 5 heads, that's quite an, fairly rare event. If you were to flip a coin 5 times, you probably wouldn't have it happen. But as the number of people performing this goes up, the likelihood that you have 5 heads goes up as well. So if you have, 40 people or 80 people all flipping coins 5 times, then the likelihood one of them has 5 heads is now 92%. And so this is quite problematic for science, because if you have 50 groups doing the same experiment, it's fairly likely one of them will get a positive result, even if there's not a positive result to be found. So that one of them will find a significant difference, even though there's no significant difference there. And so today in research, there are a huge number of groups doing exactly the same or very similar research projects. And if you have 20 groups doing the same project, you have 50% chance that one of them will find something significant that actually isn't significant. And that's, of course, assuming they're all acting in sort of everyone's best interest and they're not throwing away data or anything like that. So if they're now really interested in publishing and showing results, then that number becomes even higher. And so the point of this is that, this sort of experiment of I flip the coin 5 times, and if I get 5 heads, that's a really rare event. I can assume something special about this coin, is really only true if you only flip it 5 times. And so the more people flipping it, the more likely it becomes that someone will find it. And so if you flip a coin continuously and say, as soon as I get 5 heads, I'll stop, you'll get 5 heads fairly with almost 100% certainty at some point if you flip the coin. long enough. And so all of these issues kind of come up that make it a lot more difficult to know what the appropriate cutoff is for saying this is a really rare event. So you could go and say, instead of 5%, we'll take 1%. But it still doesn't change the fact that if there's lots of different people trying to do these experiments, that unless your threshold is really incredibly low, it's unlikely, or there's a huge likelihood you'll get false positives in sort of your detection of real exciting results. And so what we have here is this idea of, and so clearly this is not the case. So we could keep flipping coins and ask all of our friends to flip coins until we got 5 heads, and then publish results that look, we have a statistically significant difference in the number of heads that we get with the coins. And so the p-value is only meaningful when the experiment matches what we did. And so if we go back to kind of say, what did we initially look at? We didn't say the chance of getting 5 heads ever was less than 5%. We said that if we had exactly 5 observations and all of them are heads, the likelihood that a fair coin produced that result is less than 5%. And so that those two statements are very different statements and have very different implications. And so it's quite difficult to kind of internalize this, because really what it means is that when you're doing tests and you're doing statistical analysis, you kind of have to keep track of all the things you've already checked. And the more things you check, the higher the barrier is for you to accept something you find as a new exciting result. And so what this means is kind of you have to scale by P, or by the number of things that you check. And so if you just do one experiment with 5 observations and you get 5 heads, then that's significant. But if you do 50 experiments, then you have to make that cutoff 5 times more difficult in order to have the same level of, 50 times more difficult in order to have the same level of statistical significance. And so this is really bad news for us and this class, because what we really focused on initially was how can we quantify all sorts of interesting metrics. So we could calculate distance maps, we could calculate shape tensors, you could look at anisotropy, there's 10 different formulas for that. You have oblateness. If you go through some of the other lectures, we covered like distribution and some other things. And sort of the problem is, if you throw all of this data into a magical statistics algorithm, you're very likely to find significant differences between things. And so what we need to be aware of is that we're actually almost cursed by the number of different parameters we have, because there's too many places to look for statistical difference. And so if we look at, here what we do is we just simulate random data, which I find is always a good way to get a better feeling for statistics. And so here we have just 5 variables and 2 groups. And all of them are completely random. There's no difference between the groups at all. So we should never find any statistically significant differences, because it's just random noise. It's just NP random uniform. There's no signal. There's no difference between group 1 and group 2. Group 1 are just the first rows, group 2 are just the second rows. And so this is a nice basis for figuring out where are we finding lots of kind of false significance in our results. And so if we take that random table we made before with the 5 different variables, and we calculate the p-value for all those variables between group 1 and group 2, we see that we have a p-value for variable 3 of 0.0057. So even though our data is completely random, by doing this simple t-test on it, one of the variables that we found looks like it might be significant. And of course, as we start increasing the number of variables we look at, here we have 20 variables. We now have 2 that look like they're significant. We know for a fact none of them are. They're all just random noise. And of course, as we go up further and further, we see that as sort of the number of variables increases, the number of significant variables found increases as well. And so if we go there was. Oh, there it is. So that's the sort of basic chart we have where, the results become kind of more and more varied, but if you have 140 different variables that you examine, you're likely to find 8 that are statistically significant in your data set. And so we can correct for this, where we can say, there's a cutoff and that we make the cutoff more difficult. And so this is called Bonferroni correction, by dividing it by the number of tests that we perform, or multiplying the p-value that we get by that number of tests. And so what that does quite nicely here is that we take the number of significant variables found, and it kind of flattens that curve. And so now the number of significant variables found is constant, even as we have more and more variables in our system. Can anyone think of why this might be bad? Or what the problem with this is? This seems to solve it. We don't find any more statistical significance, even though we're looking at 140 different variables. Should you just do Bonferroni correction all the time, and then you can analyze as many variables as you want? Yeah. So that's exactly the problem that you run into by dividing dividing by the number of samples you do, you make it harder and harder to see actual differences in your data. And so if we go here, where we start off with, we add this correction factor, it's a great solution, but what if we actually have a difference we're interested in? And so here we make a synthetic data set where it's centered at 0 and then centered at 1. So we have group 1 and group 2, and there is actually a difference between them. We've made it that way. We know there's a difference. We want to find it. This could be healthy and sick or whatever else it is. If we now add this to a table and perform analysis on it with more and more variables, what happens is that it gets harder and harder. Does it show us that? It gets harder and harder for us. So these curves don't show that very well. But it gets harder and harder or more difficult to get a significant p-value for that measurement that we're looking at. And so if we only look at one variable, so if all we focus on is the variable that's actually different, we see that almost all the time we get a significant difference. So when we run our analysis, we get a significant difference. As we start to add more and more variables to this, we see that we get more and more insignificant results. So that by making it harder and harder for us to find significant results, it makes it harder to see this in our data. And so what this means for us is we have a really different variable, and the more variables we check, the lower this number drops down. And so if we only check one variable, there's a 95% chance we'll find statistically significant differences when we look at it. If we now look at 100 variables, that drops down to 40, or 45% or something. Which means for you, if you're a PhD student, you spend all this time doing an experiment, and then you check 1,000 variables, there could be results that you had in there that you now have lost because you've had to make your threshold so high because you just dumped all your data into it. And so the result for this is that you need to be, each variable that you check costs you something and that you can't go undo that. So you can't be, I'll check all 100 variables and then I'll take the ones that are significant and just say I checked those, so I only have to correct for that at the end. Because by taking all the variables at the beginning, you've kind of checked, you've used up that statistical credit, sort of, and can't go back to the point you were at before. And so it means that when you're doing these sort of experiments, you want to be prioritizing which variables you're checking, because if you don't, you'll end up sort of losing a lot of potential interesting results because you just dump the data in. And so if you have no idea what variables are interesting, then maybe dump, and you have tons and tons of data, then of course you can afford to just dump it all in. But if you know something about which variables are probably interesting, then it makes sense to only investigate those and not to include every possible variable you can, because you'll make it a lot harder for yourself to get significant results. And so this is the concept that's really quite difficult to grasp, because it's sort of an analysis that has memory. And so you can't kind of go back to what was happening before you did the analysis. And it's, quite important that you sort of internalize that, because this is what makes statistics challenging and difficult, and is what's quite important about designing your experiments and picking what you're going to measure and choosing variables that make sense. Because once you've done this, you can't go back to the point where you only look at one variable. Are there questions on that? Okay, so the predicting and validating we'll sort of skip over because we've covered it already fairly well. And the other slides, for whatever reason, didn't compile. So we can go over the old ones, which we'll have a link to in the presentation, where it's sort of this idea of parameters and image processing. And so here, you have your raw images going in. You then have a Gaussian filter with 0.5 sigma, 3x3 neighborhood. You then go into a threshold. You have your threshold value coming in, your shape analysis, and your thickness analysis coming out. So this kind of gets back to that sort of directed acyclical graph approaches that we talked before, where you can just sort of draw out what does your analysis look like, what's flowing in, and what's coming out. And so this is sort of a very simple analysis. Where this starts to get a lot messier is where we now start having lots of different choices to make. And so we have a raw image coming in. We now have a Gaussian filter, a median filter, a diffusion filter, no filter, Laplacian filter, wavelet filters, everything else. And then you might have a normal threshold, hysteresis threshold, automated threshold, deep learning threshold, any number of other things. And then you have all of those flowing into all of your next analyses. And so you can end up with processing chains that are quite complicated. And of course, once you add parameters to this then gets even worse. So you now have, a Gaussian filter with 0.5, with 1.2, with 1.0, with a 3x3 neighborhood, a 5x5, all of these other parameters that can come in. And sort of how do you get a grasp of what analysis you're actually performing and what things actually work well. So we covered the ROC curve as a way of sort of evaluating how well is your segmentation working. But once we move beyond that to a lot of other different parameters, it becomes a lot more difficult to even define what an ROC curve would be showing you. And so we have this idea of kind of qualitative versus quantitative. And so, a qualitative assessment is, looking at the structures that you get out, comparing expectations from sort of other independent techniques or approaches, trying to imagine before you do your analysis what the data should look like, and comparing what you see, what are artifacts come up, do shapes look correct, are distributions and orientations meaningful? And so, in this example here, we have, 3 different results. with 3 different threshold parameters that we've given. And so, do you expect the structure to be just this sort of network of pipes inside your bone? Or do you expect there to be lots of holes and cells as well? And that, you could do all sorts of quantitative analysis and trying to determine which one's better, but fundamentally you should have an idea if you're looking for the pipes or if you're looking for the pipes and all of the cells and how many cells there should be and how they should be distributed around. And that by qualitatively looking at your image, you get a very quick impression of what things might be going wrong, what things might be included that shouldn't be. That's a lot harder to get with a sort of quantitative analysis. Then the quantitative approach for this, so this idea of sort of parameter sweeps. And so what you can do is you can sort of take an analysis, and here it's, how many cells do we find? And what are the volume of those cells versus what's the threshold value that we give it. And so that you can see kind of the mean cell volume goes down and then maybe starts to go up a little bit. And the number of cells kind of fluctuates quite a bit based on what threshold we give into our analysis. And so by making curves like this, where you're able to change the parameters and look at the output of your system, it makes it a lot easier for you to decide which parameters sort of make sense and which ones give you kind of the best, most stable result. And so of course you can look at other things. You can look at like orientation, volume, everything else. And one of the easiest analyses to do with this is just this idea of sensitivity. So where you make that curve and you sort of look how much does your metric that you're interested in measuring change based on how much does your parameter change. And so if you don't really worry about the units of this, just worry about sort of the consistency of it. But basically if your parameter changes a little bit and your number goes way up or way down, then this is a very sensitive parameter. And so you're probably not at a very good point because slightly more noise or slightly less noise is going to change your result a lot. And if you're at a point where, the parameter can change quite a bit and the metric stays constant, then that's a very stable point in the curve to be. And so, if we look at sort of an object count curve, we can think of the sensitivity as just the slope. And so if you were to look at this curve, obviously, you'd want to know what images looked like at this point to know if they're actually counting the right things, but where would you want to measure? Any idea? Right. Right. So exactly down here, if you change your threshold by, 100, your object count doesn't really change that much at all. And if you're over here and you change your threshold by 100, it's sort of a direct slope up. And so here the sensitivity is fairly high, and here the sensitivity is fairly low. And so you want to focus on picking points where the parameters you're most interested in aren't that sensitive. Because if you're trying to calculate sort of like your ICC values and how reproducible your results are, and you're in this high sensitivity range, then it's very likely that different measurements will get, or even measurements of the same sample will get different results because noise or something else being slightly different. And if you're down at that part, you get much more stable results. And often you end up with situations where these, you're looking at a number of different parameters where you'll have sort of anisotropy, count, volume. And here we see, these curves all have different shapes, but they're all fairly flat in the same position. And so this lets us say we want to operate at this position because that's where these values have this flattest change. If you were just focused on count, it might almost be better to measure here because it's very flat there as well. But kind of looking at all the different parameters you have to account for, this is the position that sort of makes the most sense for the measurements that you're doing. And so, of course, a lot of this involves deciding which metrics are more important, but that depends a lot on what you're trying to assess. If you're counting cells, then count is probably the most important one, but if you're trying to find malaria, and malaria cells are very anisotropic and normal cells are not, then you'll need to kind of take into account multiple variables because you want to just not find cells, but you want to be able to tell something about their shape. So then the last thing we'll cover today, and then we'll do some of the visualization slides next week, is this sort of idea of unit testing. So has anyone heard of unit testing before? 2 people. And has anyone done unit testing before? The same 2, 3? Okay. So anyone from computer science, I sort of would expected to have heard of this. Computer or software engineering as well. It's sort of one of the most important aspects of software development. And so the idea is that when you write these huge, giant applications, like image analysis or operating systems or self-driving cars, that you want to be very confident that the code that you wrote actually works. And that one of the things that engineering has done very well is appreciate how bad people are at building complex systems. So that rather than say, all of our engineers are brilliant, and so we trust them to write code that works, they say we want to have lots and lots of tests because even though they're brilliant, they still make lots and lots of mistakes. And so what this is this whole idea of trying to make sure you break up your tools into small little pieces and test each one of those pieces so that they work well. And so unit testing is possible with every language. Most have sort of built-in tools that make it very easy for you to use. Even MATLAB has fairly recently introduced the ability to do this. And the built-in tools sort of make your life much easier. And sort of the idea is that each part of code can be tested independently, and so you can make sure that each function or each little piece works well. This is also quite good because if you've tested each little piece, you can then take a Gaussian filter that you have and replace it with a super fast GPU Gaussian filter, and you can be confident that it works because the same tests are run on both. And so if it passes your test, then it should work. It also can then be sort of combined into more complex analyses. And so a lot of times you'll test all the individual pieces, but you also want to test that all the pieces, when you put them together, work as well. And so ideally, this is done with sort of realistic but simulated test data. And so this is where you kind of will generate data to run your test so that you are confident that your tool works. Obviously, if you have a data set that's 14 gigabytes in size, you don't want to have a unit test that takes 4 hours to run every time you update your code. You want a much smaller piece that gives you an idea if your code's giving the right results, and that maybe you have an integration test later that runs a much sort of bigger, more complicated one. But here, sort of in the MATLAB world, what this looks like is that you can sort of have a function. You can write the following tests, so test empty 2D. You can do some basic things in it, and that you can cover sort of all of the different possibilities for fairly simple scenarios using this sort of assert command. And so assert comes up in tests all the time, and basically what it says is, I expect this thing to be equal to this thing. And so that can be images or outputs or values or true or false, but that you have these kind of assert statements all around, and that's how you write sort of tests. And so if you look, image J, hopefully, yeah, this is, for people who don't know Java, potentially slightly complicated, but that if you go through the image J source code, there's tests all over the place that, if you make a new virtual snack, that it's not null, so that it's valid. That if you change the color model of a virtual snack, that works. That if you add a new image, that it's still there. If you remove the image, that it's gone. If you add, delete slice, get the pixels, that the pixels that you get are actually the pixels that you expect to get. And so all of the basic functionality gets tested through tools like this. And that's how it looks for Java. For KNIME, what you have is you have sort of these little blocks that you put in your workflow, where you have like these difference checkers to make sure that your workflow gives the outputs that you expect. And you can have that sort of run in the background to make sure your workflow is doing what you expect it to do. In Python, you sort of have unit tests with PyTest. And so if you look at a project like scikit image, you can click on these links and see that, for watershed, they actually come up with a test image. With markers, they run the output and they make sure that the watershed output is equal to what they expect it to be. And so they sort of do this problem by hand, where we know if we give it this input with this marker, that that's what the output should be. And you can go through, all of the different test examples that they have in order to make sure that this code works. And what's quite nice about this is now if someone else comes up with a faster, better implementation of Watershed, or wants to change how Watershed works to use less memory, that you can make a request to them, and they'll say, well, as soon as all the tests pass, then we'll accept the request to our project. And they don't have to manually go through and check for every possible bug that your code could include. Similarly, for connected components, that you have sort of all of these test images that you put in. One of the tests that I find sort of more useful or more practical for classes like this is this idea of doc tests. And so here in Python, you can make a string after you have a function by doing these 3 quotation marks, and that you can then have code that runs inside your function that explains what the input and the output should look like. So you have this text here which sort of describes what your function should do, a list of what parameters go in and out, some explanation of the return, and then you have actual code. And so what you say is if you run this function on this image with values 1.5 and 2.5, then you should get out 0, 1, 1, 1, 0, 0, 0, 1, 1. And so that they make it quite clear, what kind of input your function takes, how it's formatted, and what the output looks like. And so you can do this in Jupyter as well, so with notebooks, where you could make a function and just use this auto test, which we define up here, where you say, function adds 5 to the result. Add 5, 5, 10, return x plus 5. And so it will then run to make sure add 5, 5 gives us 10. And if we say it's supposed to give us 11, or we say it's plus 6, then we see that it's failed. So that our function doesn't get the result that it's supposed to get. And so it makes it, clearly a very simple example, but it checks that it actually does what it's supposed to. If we now do something like simple label, where it basically just runs scikit-image.label, we want to make sure that if we give it an image that's, MPY, which is just a diagonal with 1s across the diagonal, 3 by 3, and we run, this is what the test image looks like, and if we perform simple label, then we get 1s, everything's connected, and that's what our output looks like. If we then turn the middle point off, then we should get group 1 here and group 2 there. And so we can run this and we can see that it does every single check and that it matches all of our outputs that we expect to get. And that if we did something different, so if we didn't do label, if we just return the image itself, that it would pass the first tests. That it would pass the first tests, and that it would then fail the second test because it didn't actually do the labeling, it just gave back the image it gave before. And so you can easily sort of go through and make these kind of tests inside of your code. And obviously you shouldn't test that label works because there's already tests someone else has written that make sure label works. But once you start doing more complicated operations, to test that you're actually measuring and counting the things that you're interested in. So if you're trying to count the objects that are touching each other, then having a few simple examples where objects are touching each other and you count them correctly, first of all, gives you confidence that your code works. And it's also then very useful for someone else who wants to use it because they can see what conditions you've actually checked your code for and know if it's reliable for them. And so when you're using new projects in Python or KNIME or any of those tools, it's important to kind of understand what tests they've used to know if you're using tools that someone else has checked or if you're just kind of using something that might work today and might break tomorrow. And so this is how you give yourself a lot more confidence that what you're doing sort of works. So MATLAB has this before. They have explanations there on that site. Test-driven programming is sort of this next step where rather than sort of start off and write a ton of code to do your analysis, you start off by defining what tests you need to do. So if you look at how banks, insurance companies, or large companies in general solve problems, they usually come up with a list of tests that the code needs to pass, and then write the code that will pass the tests, rather than writing a bunch of code first and then testing everything later. And so here you'll often get this, from business requirements or a product manager where they say, shape analysis needs to give anisotropy of 0 if you give it a sphere. The center of volume needs to be within 0.5 pixels, and the shape analysis should run on 1,000 by 1,000 image in 30 seconds. And so that you'll have tests that test all of those different conditions, and you make those first, and once all those tests pass with your code, then your code's done. And obviously there's style guidelines and things that you can try to follow, but that it makes it very clear when your task is done, because once you've passed all those tests, then you're finished. Versus if you write a bunch of code and then someone has to decide, did your code do what it was supposed to do? Is it secure enough? Does it run well? Could we make it more performant, that you make it a lot easier if you just say, here are the tests that need to be passed, and as soon as you pass them, you're done. And if you can't pass them, then you change the task. But that you have this sort of operation mode of really thinking, what are the tests I need to make in order for my tool to work? And then the idea of continuous integration is where you have this running all the time. And so for QBI, it's currently not a great example of this. But if you go and look at all the different versions, oh, okay, no, it's working now. You can see that for each upload, it checks with Circle CI and Travis, which are two tools that sort of run continuous integration, that all of the slides execute without any problems or mistakes, and that you can click on like lecture 9 and see that this build failed. And so if you click on it, you can see what didn't work, and you can see the whole history of the project. And so you can see here it's taking all of the notebooks and all of the slides and compiling them, and that at the very end you can see if there's what problems it ran into. So here looks like it ran into some TensorFlow related problems. It couldn't open up any more libraries, but that you basically can be confident that it worked correctly because all of the notebooks were able to run. Yeah.
And also, where does it actually run?
So it runs all in the cloud.
Yeah.
So Circle CI and Travis are both commercial companies. Microsoft has something on Azure that does this as well. I'm not familiar with that one. But for open source or any project that's public on GitHub or GitLab or what's the other one? Bitbucket, you can have this connected to your project. And anytime you make a change, it'll start running all of the tests.
Okay, but for example, what if I had a package in my notebook? For example, we just made one 4-hour project because running it over Kaggle was a bit of a mess.
Yeah.
So we put it into a big package.
Yeah.
But then you also need to like, couldn't that somehow break in that thing? Like, I'm not really sure, but like it seems really fragile. Or
Um,
is it or is it like super robust? Because I just sometimes when I run the possible size on my own machine, then it's different Python environment.
right. Yeah, of course.
And
But
then it
you,
breaks.
but so with Circle CI, you describe and Travis, both of them, you say exactly what your environment looks like.
Oh,
And so, I mean, what's nice is that it's you set up the environment, but it's not your laptop. And so every time it runs one of these tests, it sets up a new environment from scratch, installs all the packages that need to be installed, and tries to run it.
what's the difference between Circle CI and Kaggle? I know that Kaggle is much more, but the Kaggle kernel.
Well, so Kaggle doesn't have any tests or anything like that in it. So Circle CI is made to just take like your project or your repository, your code, and run it. Kaggle kernels is meant for like you to develop and do analysis. And so this is much more if you like were to make a package and you want other people to contribute to it, that if we go to like kind of the extreme example, like TensorFlow. So this is a huge project that has 2,000 different contributors, 27 branches, 79 releases, and 53,000 commits. And so this is a project being worked on by thousands of teams all over the world in order to make sure it has all the features and all the compatibility and works on all the different systems. And so what you do if you want to make a change to TensorFlow is you make something called like a pull request. So here, updating the README is pretty minimal. But if you go, I think I have pull request, my pull request, closed. So this was then for something with TensorFlow Lite, which is then a little package of it. It's then quite small. But what you can see is, it's quite intense what they have set up. So they have much more set up than. Yeah. So if you, oh, you can't see all of them there? Yeah, so here you see more of them, that they test it for, that when they build TensorFlow on Android, that it works, that they can build it on Linux, on Ubuntu, on, what are the first ones? Do you have them in separate groups? On Mac, on Windows, on all of these different platforms, and that they check that for every single change that gets made, and that's the only way you can manage a project that has 2,000 contributors.
For concrete questions, but can you match Kaggle kernel to a Circle CI kernel or environment?
Mm-hmm.
Because we had some problems where it's really only feasible for us to do everything in Kaggle because the data set is so big.
Yeah.
And then when you download it, it's maybe a different environment or whatever.
Yeah.
But if you could keep it all in the cloud and you just specify the environment.
Yeah.
Could you then do the test on Circle CI and keep the development or whatever analysis on Kaggle?
Well, what you could do is you could build a package. So they're quite different systems, but if you were to make a package, you could put it on GitHub and have Circle CI check to make sure your package works. And then you can install that package in Kaggle.
Yeah, we have that now.
Yeah.
It's just not being checked for the tests.
Right. And so Circle CI doesn't make any tests for you.
No,
You have to tell it
no,
everything
no.
you want to test. Yeah. But that runs all those tests to make sure it's quite consistent. And then it's helpful because it can let someone else come and edit your code and immediately see if the tests worked or not. And so that's really what it's useful for. So it's slightly different from Kaggle, but like almost all the packages in Kaggle are being tested by CircleCI or Travis or one of these tools. Because it's just, with any large complicated project, you see scikit image is the same way, where you go to this and you can look at any of the pull requests that come up, and this little X means it hasn't passed all the tests. And so of course, until it passes all the tests, they're not going to accept it. And so here we add axes, or this is what this person does. And you can go through and see here, this is complaining that you haven't formatted your code very well. So you used spaces instead of tabs. You have lines that are too long. And this is just a little robot that yells at you. And then you have sort of the tests here where it's just CircleCI and appver. And so you can go there and you can see what exactly was run, where did it fail. They check it on Python 2, Python 3, on Mac using sort of Xcode. Then they have other systems to test it on Windows, but that you can kind of see this seems to work on a number of different environments well. And so we're fairly confident that the code is good. Otherwise you'd have to manually install all these versions of Python, manually go to a Mac, to a Windows, to a Linux machine, and make sure that they all work the same way. And so with tools like this, you just make it a lot easier. So for most of you, you're working on projects, you probably won't have time to set all this stuff up, but it's quite useful to at least know that it exists and that you should be doing it once your project gets much bigger, because it's quite important to make sure results are reliable and stable, and that you'll look at scikit image or TensorFlow and they're updated every week. And so if they're being updated all the time, you want to make sure that your results aren't changing when they're updated, that your notebooks and everything still work, and that like even with this course, in scikit image, they renamed some functions, and so half of my slides broke between last year and this year. And I could have manually figured that out by going through the slides one at a time, but because of CircleCI, I just get an email that said, half of your slides don't compile anymore, you need to fix bugs. Which then makes it easy for me to know that those slides are broken. It doesn't fix all your problems, but it at least lets me know that on a standard environment that I don't control, things still work. And so yeah, it's just a very useful environment for testing those kinds of things and keeping sort of projects working well. You then also have kind of the last thing that comes up, which is this idea of code coverage. And so here you can see for this project that you have sort of this little badge which says it's passed all its tests, and code coverage is 82%. And so with Python, and again most languages, you have this where you can see each file in the project, like easy dash, that 71% of all the lines in that are actually being run when you do tests. And so here you have red lines on things that you're not checking. And so I never check in the tests that this error comes up when it's supposed to come up, or doesn't come up when it's not supposed to. And so this is then also a quite useful view to have, because you can go through a project and see, I have this add context function, but it's actually never being tested. And so it might not work, or it might not be set up correctly, or any number of other things could happen there. And so even though there are tests for a project, that isn't being tested anywhere. And so if someone is going to use it, they should probably make sure it's tested themselves. It's then also quite nice because if you make changes to projects and this number goes down, then you can tell someone, well, we won't accept the change until you bring that number back up to where it was before, or ideally even higher, because we don't want to have a huge amount of code in the repository that's not being tested by anything, because that code can break or have something go wrong with it, and that's not something you want to have happen. And that kind of the last thing with this is, for PhD students or data scientists, a lot of times people say that, writing code is sort of what you have to do, and doing tests, that's for software engineers who are working on massive projects. And that's really not the case at all, because if you're doing data science or you're doing research projects and your code doesn't do what you think it does, then you're wasting your time. So having code that's sloppy and doesn't work or doesn't do what you think it does or gives wrong results or is unstable isn't helping you do your science project, because if your code's bad, then your analysis and everything else you're doing is going to be bad as well. And so it's quite important to have good code. You don't need to have 100% test coverage or tests for every simple possible case that might come up. But if you don't have any tests, there's a very good likelihood that you're doing something incorrectly. And even in the groups I've worked with, we've had code that we were using for, I think, 10, 15 years that they found very serious bugs in afterwards. So all the reconstructions that were done with it had problems with them. They looked fine, but because no one ever wrote any reasonable tests for it, they gave the wrong results. And so it's quite important that if you're doing things and you want your results to be meaningful, that you at least make some tests so that you're confident that it's working. And if you look at these slides, it's not super difficult to make simple few little tests and just have them sort of sprinkled around your code somewhere. That you don't need to come up with huge test libraries. You don't even need to use Circle CI. You can use this sort of auto test in Kaggle by just copying and pasting that block there, and that you can then have your own tests, and that anything that starts off with these 3 lines, it assumes is code that you want to run. And so just having very simple starting points will give you a lot sort of more reliability with what you're doing, and ensure that your projects are at least somewhat reproducible, and that your complex functions are kind of doing the right thing. And that most of you probably do this a little bit anyways, that you'll run it on a simple image and check the results. And the advantage of this is just all automatic, which means that you are able to see the results kind of automatically, and every time you change a single line in your function, the test gets rerun to know that you still get reliable results. And so, yeah, that covers all of that. Yeah.
Just one question. These tests run every time we run the code, right?
Yeah.
So like for the case where we are actually running with our data,
Yeah.
we deactivate them, or how does it work? Does it run the test and it's also running our data?
No. So when you do this, it runs the test just when you define the function. So if you run add 5, it just runs the test right there. If you now run add 5 again, down here, something like that. That it doesn't run that test again. So you see it ran it just once here, and then it runs your function. And if you run this, it only runs that test once. And so it doesn't hurt your performance at all to have the test there. It's just helpful. But if you're moving it into like a package, you then don't need the auto test anymore. So the auto test is just inside notebooks, so you can have it run the test for you. Once it's in a package, you can use doctest and pytest to run it for you. But this is just to kind of force or help you make tests on the way. Otherwise, you'll end up having all this code that you've written, and then you try to sort of move in to a package development environment, and you have no tests for everything, and you have to write all your tests kind of from scratch. And so that then gets quite time consuming and sort of is not a useful use of resources when you can make just little tests on the way to make sure your functions are kind of doing the right thing.